Hello there and welcome back to this video series on control systems. We have started looking into frequency response methods in the previous video, and to be specific, we have seen why we need to study frequency response methods and what is the important feature of frequency response methods, and we saw that the frequency response data can be shown either as a polar plot or as a Bode plot. This Bode plot, we use plural Bode plots because it involves two graphs, one graph omega versus magnitude ratio and another omega versus phase angle. With that said, in this video we'll try to see topics such as frequency response of a first order system and frequency response of a second order system. Then we'll slowly shift gears and see what is Nyquist plot, what is how we read gain margin, phase margin from Bode plot, and so on. We'll begin by looking at first order system and obtain its frequency response. Let us consider a first order system given over here, k over tau s plus 1. We know this k is the gain, tau is the time constant. Given a transfer function, we can very easily obtain the frequency response for that system by simply setting s is equal to j omega in this transfer function. So g of j omega is k by, in place of s, substitute j omega, j tau omega plus 1. So its magnitude can be obtained by magnitude of k divided by magnitude of this complex quantity in the denominator, that is k divided by under square root tau square omega square plus 1. Real part square plus imaginary part square tau square omega square. And its phase angle can be obtained as phase of the numerator minus phase of the denominator tan inverse tau omega. To draw the Bode plot, you take logarithm multiplied by 20 to get the magnitude ratio in decibels, which is all this expression which we got from this k over so and so, 20 log k minus 20 log square root of so and so. Okay. We see what happens at very low frequencies. Very low frequencies, tau tends to 0. So this whole expression, it becomes 20 log to the base 1, which is 0. So it is 20 log to the base 10 k. At very high frequencies, this m tends to infinity, because when omega tends to infinity, it becomes very big. Similarly, at low frequencies, omega is very small, this angle is 0. When omega is very big, tan inverse infinity is minus 90. That's what we observe here. Noticing this, Bode plot may be drawn as shown in the next slide. To be specific, we use numbers k is equal to 10 and tau is equal to 0.1 to simulate the system and draw the plot as shown here. Okay, 10 by 0.1 s plus 1. So this part, low frequency part, is a flat curve, and then it is coming down approximately at a slope of 20 decibels per decade. We'll see what this means in subsequent classes. If you don't get it, don't really worry now. This is the phase plot. Then we try to draw the polar plot also for the first order system and show the response. All this is standard part. You substitute s is equal to j omega. You obtain magnitude and phase. The polar plot, the way we use this data is slightly different. For k is equal to 10 and tau is equal to 0.1, polar plot is drawn and shown. You can notice that the angle is negative throughout, and magnitude is 10 when omega is very small, and is tending to infinity when it is omega tends to 0. Okay. Likewise, phi tends to 0 when omega tends to 0 and approaches minus 90 when omega tends to infinity. Drawing this polar plot may be a little bit tricky. It may be slightly confusing to begin with, but I'm sure if you practice one or two plots, it will be as easy as a piece of cake. The plot shown in the next slide is drawn using octave. Okay, you can see that when omega is very small, the plot started here. You can see the arrows going, and it ends at 0 origin. You can see that for first order system, the entire polar plot lies in the 4th quadrant. You can see in the case of second order system that it comes into the 3rd quadrant also. You can see the animation. You compute each magnitude, I'll go back and show it again. You compute each angle, at that angle plot magnitude, and so on. These points are formed and you draw the graph. You can see that when omega tends to infinity, the angle is minus 90 degrees. It is acting down. This angle is minus 90. I will very quickly see the frequency response of second order system also, and then continue with Nyquist criterion. If it is not really very clear, don't worry about it. Just remember what we are doing, and then we'll come back to it at some point of time. You substitute S is equal to j omega, and you'll get such a transfer function, and you substitute lambda is omega over omega n, and you get this. Okay, we'll find the magnitude in phase and compute the frequency response. Okay, m is given here, that is magnitude ratio, and this m is maximum when the denominator is minimum, that is when the quantity under the square root is minimum, which implies this whole thing is minimum. So we say differentiate that and say lambda is 1 over, lambda is under square root 1 minus 2 epsilon square. Okay, so this is maximum when lambda is omega by omega n, which is under root 1 minus 2 xi square. This frequency omega r shown here is called the resonant frequency, and the value of m at omega is equal to omega r. If you substitute this omega n in m, you get mr, resonant peak. That is, you take this value of omega r and substitute in here. You get resonant peak. Okay. The angle is given by tan inverse, imaginary part by real part, and we show Bode plots as a sample for a specific value of omega n is 10 and epsilon is equal to 2. These are shown over here. Again, these plots are obtained using octave. We'll see how we do this manually. That is, we'll try to plot a couple of Bode plots and convince ourselves that this is in fact the case. Similarly, we draw the polar plot. Again, this plot is again drawn using octave. You can see that the angle goes to minus 180 degrees when omega tends to infinity. Just like we specified what is rise time, peak overshoot, and settling time, you have something similar in frequency response. You have resonant frequency, resonant peak, gain margin, phase margin, bandwidth, and gain crossover frequency. Along with this, of course, you have phase crossover frequency. These specifications, they constitute frequency response specifications. In design, very often we specify these to tell the designer what is expected out of the system. So in summary, we say that we have seen frequency response of first order system and second order system. The polar plot of the first order system lies completely within the fourth quadrant, but part of the frequency response for second order system comes into third quadrant as well. The second order systems exhibit a resonant peak, and the magnitude of the resonant peak is completely decided by the damping ratio. Just to see what is that resonant peak, you can see this is the resonant peak. The frequency at which this is occurring is resonant frequency. Okay, this resonant peak solely depends on the damping ratio. Natural frequency did not appear here. I think that's all we have for now. Have a great day.